All right, welcome everyone, and thanks for joining us. Today's session is about bringing models to life with interactive dashboards using Dyad and Makie.jl, showing how dynamic visualization and simple UI controls can make model exploration and simulation more intuitive. Our speaker today is Anshul Sanghvi, a software engineer at JuliaHub and a contributor to Makie.jl and the Dyad platform. Anshul will walk us through the practical examples of building interactive dashboards and connecting them directly to live models. And with that, let's get started. Anshul, over to you.
All right. Hey, everyone. Yeah, thanks for joining. Basically today, going to talk about how you can use Dyad, which is JuliaHub's modeling and simulation platform, together with Makie.jl, which is a data visualization library in Julia to create some cool interactive plots and dashboards. I'll start with an introduction, then go and talk about some of the basics of how Makie itself works, which it's a bit different to other plotting libraries. Then go on to building some plots and some dashboards, right? So diagnostic plots for models. We'll do an interactive parameter sweep GUI and some interactive real-time inputs. So changing those via sliders or keyboard input. And then also some demos of cool dashboards we've made. So we've got satellite in space. We've got a simulation of a robot that's trying to stay upright, and we've got a simulation of a pumping station. And there's quite a few more. Um, also, please feel free to ask questions during the talk. Every couple of minutes, I'll take a look at the Q&A and see if I can answer things. Also, if you want clarification or if something doesn't make sense, please just drop something in there. Well, the first question is, what is this dyad thing, right? So you may have heard of Julia Sim before, or maybe the SciML ecosystem, ModelingToolkit.jl, right? Dyad is basically a platform for modeling and simulation. And so it's got this kind of thing, right? It's got a graphical interface where you have individual components that have dynamics inside them. You connect those components together to form a larger system. And it's got a graphical interface, it's got a text-based interface, and it also has an integrated AI agent, which I'll show a bit of. So at a glance, this is the sort of universe of things that you should be able to do with Dyad, right? You design your model, you can use machine learning to discover dynamics of physics or things that are going on in your model. You can calibrate your model to real data. Um, you have a control systems toolbox that you can use to build controls for physical systems. And we also have some tools to let you build very fast surrogate models. So if you have a very complicated, slow-running model, you can build a nice surrogate for that. So broadly, Dyad covers acausal plant modeling. So that's more of the, if you're familiar with Modelica, that's more that kind of thing. You can also do causal synchronous modeling for control systems or for real-time or physical systems where you only get inputs that are polled once every millisecond or something like that. Um, and there's this Dyad is also aiming to be sort of the fusion between generative AI, which is agentic AI, and the thing which you talk to it and it does what you tell it to do, and scientific AI, which is the more predictable sort of machine learning kind of thing. And those all work in harmony with each other. So there's also a video here which we'll send later about how you can use the agent to create models and things like that, but not going to spend too much time on that. So what is this Makie thing now? Makie is a visualization package and ecosystem in Julia. I think at this point, it's actually the most popular in Julia. Its big thing is that it's very easy and very cheap to update a plot live. So you can keep things, it's interactive, it's 3D, it runs very, very quick on your local machine or on the browser. You have an OpenGL backend for the desktop, you have a WebGL backend, so you can actually spin up a web server and show things. And you have a Cairo backend for this kind of publication style, vector high quality plotting. And we've also got an experimental ray tracer backend that's still in progress. But over here, and I think the brightness might get affected a bit, but there's an illustration of a NASA um, prototype airplane, which has actually been ray traced in Makie. So the exhaust plume is actually a volume plot, right? And you've got a mesh plot for this, and so it's got a lot of stuff going on. Um, Okay, so now let's go to live coding. Alrighty, so I'll send this to everyone. We'll send this out after the webinar is over, but I basically have a Dyad library which is some models which has some Dyad code in which have some Dyad code in them, right? So this is one example. And so this is Dyad code. It looks kind of like Modelica, but a bit different. It's very similar to Modeling Toolkit code. And in fact, Dyad compiles down to Modeling Toolkit. Um, and so if you're familiar with ModelingToolkit.jl, a lot of the APIs and sort of ways of doing things that we'll be using are actually we'll be using ModelingToolkit.jl things because that's the Julia representation of this model, right? So the Dyad language is a declarative language. The idea is that you're pretty constrained in what you can do, but the benefit of that is that if you do something wrong, we can tell you almost immediately without having to go in and simplify the model and so on, right? And you have a lot more information up here. So if you click on this render diagram button, you can actually go to the graphical interface, and I'm going to just automatically lay everything out. And so the idea here, zoom in a bit, is that this is a mass spring system. So you have a spring, you have a mass, the spring is fixed on one end and it's connected to the mass on the other end. And there's also a force. Oh boy, that's messing up my layout. But thankfully I have rotation. Right, so there's a spring connected to a mass. The spring is fixed on one end, but the mass also has some force that you can use as input, right? And that's again connected to a ground. And then you have a PID controller, which is going to read the distance from the velocity that the mass has on one end. And it's got some set point saying that, okay, you want to keep the velocity to some amount or something like that. And then that PID controller feeds into the force. Right. So this is the way you'd sort of build up a model in Dyad. And the PID also has a couple of other inputs. So, okay, so that's Dyad. Now let's talk about Makie. So Makie is a high-level plotting library for Julia. It's got three backends. So normally when you use Makie, you'll use one of these backend packages. You don't necessarily need to use Makie itself. There's GL Makie, which is an OpenGL backend for your desktop. There's WebGL Makie, which is a WebGL backend for the browser, right? So with that, you can actually, not only can you view plots on your local machine in the browser, you can also serve it to someone else's machine. So they can connect to a port, they can connect to some URL and they can see the plot and interact with it. Then there's also Kairomaki, which lets you give vector output to PDFs and SVGs. But since we're talking about interactive graphics, this is sort of not quite the focus. But Kairomaki is quite useful for publication style plots and that kind of thing. So in this webinar, we'll mostly focus on GLMaki, but all of these commands are all of the plot commands that we're going to use are from Makie.jl, and so they work the same across all of the backends. The backends just define sort of how you draw something, not what you, and Makie defines what you draw, if that makes sense. So, all right, I've got my Julia REPL down here, and I'm going to use GLMakie. And for this, there's a little trick I'm going to do. Which I'm going to make GLMakie's window float above this editor so that you can see it. So in order to do that, oops. All right, so time to first plot. Well, I had a warm REPL beforehand, so slightly cheating, but it's usually fast enough. So yeah, this is a simple scatter plot, right? I put in a range from 1 to 10, and I got out a scatter plot that goes from where the Y values go from 1 to 10, right? I could make this, let's say, 5 to 15. And the Y values now go from 5 to 15. The X values are sort of implicit, but you can also change those. Oops. Ah, I did. I did my math wrong, my bad there. Right. And so you might be asking, what's this fig ax plt thing? Um, so Maki, if you've used plots.jl before, for example, then you would just say, right, there's only one entity, which is the plot. And that's the same for a lot of other plotting libraries. In Maki, we made the decision to sort of forcibly create a distinction between multiple concepts. So if you look at the whole of this thing, right, and I could actually, just to make it a little more obvious, this whole window that you see here, all of the contents of this are what's called the figure. So the figure is your sort of top level object. And each of these individual boxes with, X and Y ticks, and you can zoom in and all of that, those are all, so this is one axis and this is another axis. So we call those axes. There's also other things that you can put in the layout of a figure like this. We'll get to that in a bit. And then the individual sort of traces or data plots that you see here are called plots. So this is one plot. I can add another plot to the left-hand side axis, right? So I can say I can add lines to the second axis, let's say just one below and Y, right? And so you can see these are now two different plots. So that's the distinction between an axis, a plot, and a figure. I hope that sort of makes sense. And I've also put those down here. So if you come back to this at some point, you can read about them. So all right, let's create a simple plot, right? This is just a line plot. You can plot some scatter points on top of that and create a new axis and so on. And Maki has a bunch of these sort of low-level plotting functions, right? In fact, there should be some amount of overview in the documentation, which let me zoom in a bit. I didn't enable zooming on this one, it seems. So let's see here. So yeah, there's quite a few. These are all things that you can put inside a layout like an axis, which I'll get to in a second. But there's also a lot of different plot types. So you've got you can plot an arc parameterized by degrees. You can plot arrows, bands, bar plots, so on and so forth, right? There's some cool ones. So this data shader thing is actually you pass in a lot of points, so billions and billions of points, and then Maki will sort of dynamically shade those on the GPU for you so that you can see the actual density and not just some flat display of a scatter plot, right? Then you've got the heat maps. We also have three-dimensional plots. So 3D is a pretty integral part of Maki. So I think surface is probably the traditional one that everyone's used to seeing, right? And then you of course have text plots and tooltips and so on and so forth, right? So quite a few things. You can take a look at this. I'll send the link in the chat. So the killer feature that I was talking about earlier with Maki is the ability to surgically update a single attribute of a plot at a very low cost, right? So let's look up here and see what we did. We've got one thing called PLT, which is a line plot, another thing called PLT2, which is a scatter plot, a third thing called HM, which is a heat map, right? And so, okay, let's see what could we edit here? Well, for one, we could change color, right? So let's say plt.color. And you'll see that this is not actually a single value. This is this computed node kind of thing. And so, but the nice thing about this is we can say plt.color equals red. And voila, now the line is red, right? And so that the plot's still displaying, I didn't have to redisplay, nothing had to be redisplayed. Very little had to be recomputed. Basically, we just sent a signal to the GPU saying, okay, the color of this line is red now, right? Similarly, I could also change the data of that line plot, right? So I'm saying the first argument of the line plot should be another set of random numbers. Boom, there you go, the data changed, right? Similarly, the axis is also updatable. So I can give it a title, and now you see there's a title up here. So all of these things can be updated very quickly. You can do it in a loop. You can do it in a recording to create a video, right? And so this is sort of what I think of as the killer feature of Maki. So let's go for a little more complex example. So let's make a plot. So there's a plot type called scatter lines, which basically just contains a line plot and a scatter plot, right? So the other thing about Maki is that plots are plots can contain other plots. And so you can build this very rich tree of different abstractions. And so in this case, I have a PLT, which is a plot object of scatter lines, but plt.plots contains a line plot, which is this thing, and a scatter plot, which is this thing, right? So I can update the color attribute of the top level plot, and that just makes everything red. But I could also update the color attribute of one of the subplots or one of the child plots, right? And so in this case, I chose plt.plots1, which is a line plot, and I updated the color there. So that became green, but the other one stayed red. Now, if I update the color at the top level again, I would have expected that to pass down. I guess not. Probably because I explicitly updated this. That would make sense. Yeah, you can also update multiple attributes at once, right? So it's not just that you're restricted to doing a single thing at a time. For example, if I wanted to update my data and my color at the same time, you can use this update exclamation mark function, right? And so you'll notice that this changed both plots colors and it also changed the data. Now, what if I wanted to change the color to an array of colors? Right? So this expression is an array comprehension that's going to get me a vector of this RGB type. But if I do this, Maki actually complains. So this is one limitation that you should be aware of sort of before you go building crazy dashboards, is that generally you'll be kind of restricted to the type that you passed. When you're updating an attribute, you're kind of restricted to the type that you passed in. So let me give you an example. If I said here, if I gave a vector of colors 1 per point when I created the plot, then running this update would fail. But this would be okay. And then similarly, I could actually make these different colors per point, right? And so you can see that gradient kind of happening. So yeah, okay, so let's now sort of reset this because I want to show something different. All right, let's update this plot live. So we'll go in a loop, right? And for 10 iterations, every second, we're going to change the color to something else. And so you change the color, you sleep for a second, you change the color, you sleep for a second. That happens 10 times, right? And you can see that now every second, this is slowly moving from green to red. And at the end of 10 seconds, that will become fully red. So that is the simplest possible animation you can make. And that's pretty simple, right? But this approach of a loop can be a bit slow because obviously you block out anything else from running in your Julia REPL at the same time, right? You're sort of consuming you're blocking anything else from running on the main thread with the sleep function. So let's instead use Maki's events formulation. So every figure at the top level has a bunch of these different events. So you've got the window area, you've got the DPI, you can check whether it's open. Whenever you click a mouse button, right, it fires an event. Whenever you scroll, it fires an event. And in fact, these events are how all of the zooming logic is implemented. So you can do something triggered when your mouse position changes, when you click a button, when you scroll, when you click a keyboard button, even when you drop a file into the window, for example. But one of these events is the tick. And so the tick is basically every time that the screen is drawn to. So that's basically every time a frame is drawn, if you think of the frame rate of a video game, for example, this is effectively every time a frame is drawn, this function is going to fire. And so you'll see we have this variable called current dt on the outside. So I keep track of the current dt, and if the current dt is greater than 1, then I change the color. And so I can run this. Oh no, what happened here? Ah, right, I forgot to define current dt after talking about it. Right. Hmm. Whoops. Not entirely sure what I did there. Let me see. All right, so I create a new plot, new dt. Ah, there we go. Okay, yeah. So every second you can see the color is now changing. And I can let's say I want the line to be a bit thicker so you can see it, right? I just said in my REPL, I just said, okay, the plot line width should be 3, and boom, it updated. So yeah, that's the kind of cool stuff you can do. You can also turn, so this on function, events of fig.tick is what's called an observable. And so an observable basically um, knows when it gets updated. And whenever it gets updated, it stores all of these listener functions inside it. And whenever it gets updated, it'll run every listener function that's registered to it, right? And so basically, every time that the render tick happens, this tick observable gets updated. That calls this function that we've defined in here. And but you can also turn, if you have a handle to that function, you can also turn that function off. And similarly, you can also change the data. Ah, okay, so did I do something? Yes, okay. Right, I wanted this formulation for a reason. So let's say, every certain amount of time, you want to change the data to something different. And there you go. Now the data is changing every second. So now you might be wondering, you can do this live, but how can you make an animation, right? How could you record a video of this happening? And animations are fortunately extremely simple. Um, you do effectively the same thing. So you can change an observable, or you can use the update function, but you do that within this record function. And so what this record function does is you give it a figure, you give it the name of the file, and you can optionally give it some range of values that you want it to iterate through. And then you can also specify a bunch of other things. You can specify video codec, frame rate, so on and so forth. And inside that, this will basically loop through all of these values. So this is the equivalent of doing, for I in 1 to 30, and then execute this function body. So let's run this. So this is a spiral, right? Is the plot that I have right now. So that took about 1 second initially. You'll notice that it's 61% compile time. If I run it again, that took about 0.3 seconds. And that's for 30 frames, right? So animation in Makie is very, very fast. Let's take a look at this video. So for the first 10 frames, the color changes, and then for the next 10 frames, you can see that the line sort of advances slowly along its path. All right. So does this whole concept of sort of observables make sense to everyone? I don't know if we can do like a show of hands or show of thumbs ups or something.
Yeah, yeah, they can type something in the chat box.
Yeah. Is there a way to allow someone to speak, maybe if they have their
Yeah,
hand
yeah.
up? Just out
And
of
they can
curiosity.
raise their hand. They can raise their hands, and
Ah,
then
sweet.
yeah.
Okay. So, yeah, okay. So, yeah, yeah, yeah. So if anyone raises their hands, then we'll take that as a sign to sort of stop. Alrighty. Bernard, I think you had a question. You might have to type it into the chat box, though, into the Q&A, though. Ah, sweet. So the response was just acknowledging I understood, no questions there. Awesome. Okay. So now that the basics are sort of set, moving on ahead, the figure also contains this thing called a grid layout. So that's basically like um, I mean, it's what it says on the tin, right? It's a layout. It's a grid-based layouting system. And let me see. So there's a nice demonstration of that here in the layout tutorial on the Makie docs. But basically, the way you can think of this is at the top level, this figure is divided into four grid cells, right? There's one, two, three, one, two, three, and four. And the way you talk about each grid cell is you talk about its index in the layout. So this is row one, column one. This is row one, column two, row two, column one, row two, column two, right? Now, within those grid cells, you have other grid layouts. And so, for example, within this layout of subfigure A, you would have first row, which is the title, second row, which has this marginal plot and the legend, and a third row, which has the main axis and another marginal plot, right? And similarly for B, similarly for D, and so on. Even in subfigure C, this three-dimensional axis is sort of living in one cell of the layout, and then the color bar is living in another cell. And so if you sort of, let's see here. Okay, so setting up grid layouts, right? So you can see that the way they did this is they basically set up these nested grid layouts. And yeah, so in this case, actually, at the top level, there are, because it's of course a grid system, at the top level, there are three grid layouts. And then at the bottom, sorry, double check exactly what yes. So C and D share a layout, right? So this column is one layout, and then this is one cell, this is one cell. You can also merge cells, right? So it's not that think of this more of Excel rather than a matrix. Um, so yeah, but you don't have to worry about like it's not super complicated. It gets pretty intuitive. Basically, let's create a figure first, right? So this is a blank figure, and let's add a label to the top row and the first two columns. And whenever you index with a number like this, if what you're indexing into doesn't exist, then those cells get implicitly created. Okay, so I've created this super title, right? This is this huge thing. I might want to make it a bit bigger. Boom, now it's much bigger, right? So I can create two axes. For two-dimensional axes, you can also link the axis limit. So once you call this link axes function, zooming into one means zooming into the other, right? Any interaction that happens to one of the axes gets duplicated. Now I can create a grid layout for the controls that I want to use. So let's say I want to get one slider where the label is scale and it goes from 0 to 1 with a step of 0.1, 0.01, so about 100 values, right? Now there's a slider there. And you'll notice that before I ran this slider grid command, or rather, so at this point, the axes are taking up the full width of the full height of the screen. When I create a grid layout, they suddenly take up only half of the height of the screen. But when I create the slider grid, all of a sudden there's something in this control layout which is saying I am of this height. And so everything then rescales because it knows that there's only one thing of this height in the grid layout. So sometimes if you have like weird scaling issues or things don't look right, um, then that might be because of that. And so one thing you can do is you can set the tell height attribute. And now we're back to this, half and half division. And tell height basically means I should tell the layout that my height is this. Similarly, there's a tell width, which means I should tell the layout my width is this, right? And if I set that back to true, then you go back to constraining. So generally they're set pretty reasonably. But yeah, that's a thing to sort of look at. Now, there's also a lot of UI elements. So this is a grid of sliders which has, a label and it tells you the value that the slider's at. Then you also have a menu. And so in this case, I've said, okay, there's a menu with text and the actual value that it corresponds to. And the text is what shows up on your screen. So I'm creating two menus. And now let's say I want to select cosine on this menu and atan on the other menu. Sure. What I'm now going to do is show you how to connect user input from UI elements up here to plottable data. So I'm going to create two observables that contain vectors of points. And point2f basically just means point with two dimensions with element type float32. And so this on any function is effectively the equivalent of on, but for multiple observables, right? So whenever the menu selection changes and whenever the slider's value changes, so whenever either of these two changes, this runs. And this is going to update this observable with this data. So I've created these two sort of listener functions, and you can also pass observables into plotting functions. So you can either create the plot first and then update, or you can create the observable first and then pass it to the plot. Either of those is perfectly valid. And I'm just going to do two line plots of each of those. See what, okay, just needed a little nudge to update. So if you press Control click, then that sort of resets the automatic limits of the axis. So as I change the scale, right, you can see that basically just the multiplier x times the scale changes, right? So the frequency sort of increases, and you can interactively change exactly what's going on. So yeah, this is sort of what I like to call like the first and simplest GUI, right? And it's not really that much code. It's about no, that's actually not bad. It's about 30 lines of code to get this interactive thing going. So yeah, now let's get to how Dyad interacts with Makie, right? So I'm going to use my Dyad component library, and I'm going to bring in ModelingToolkit and Dyad interface, which are the two packages that you use to interface with Dyad models. And so in every Dyad component library, you get a simple thermal model called hello. And basically what this is going to do is this applies Newton's law of cooling or heating to a system where the ambient temperature is given and the initial temperature is given. And then you also have some parameterization of sort of how the heat gets transferred from your mass to the ambient, right, to the outside. And so I can construct this model, and I can run a transient analysis on this model. And that transient analysis is basically just going to that's going to run the model for a certain amount of time. Now I can just plot this result. And this can kind of take a while sometimes. Okay, so now you've got this result, right? It's an interactive screen. And you can see that the body is quickly cooling from 320 Kelvin to 300 Kelvin. But you might be asking, what is this trace? Like, which variable is it? How did it get there? And the way you answer that is we can use the function axis legend. Oh dear. Which creates a legend in the, so I've created this axis, and then I used axis legend to create a legend up here. So this is the t variable, right? And so, oops. From here, you can see that the T is the only variable here. It's the temperature. Okay, so this is simple enough. Let's make this a bit interactive, right? And so what I'm going to do here is uh, we'll give a text box. So I'm going to set up a blank figure and a grid layout, which I can put some control elements in. And then so I'm going to create this text box at this point in the layout, and I give it a placeholder value, and I say that any input must be a float 64, right? So that's the sort of validator that you put in there. And then let's see. So I'm going to create an observable. So if I oh actually okay, so let me go the simple route first. In the dyad file, there's also an analysis here called world. And that analysis has two parameters called T infinity and H. So let's parameterize T infinity here. I'll show the obvious way first, and then we can go into the sort of optimized way of how you actually do this. So, okay. So the reason I'm saying observable of any, so any is the type of what's contained in the observable. The reason I'm saying observable of any here is just because the type of result may slightly change, and you may, if you don't want to be vulnerable to that, you can do this. You can also just say, observable of, let's see, what is the type of this? Right, but you can see that's quite a bit of quite a long type. But I could just give it an abstract type, and that would work equally well. Oh dear. Oh boy. Yeah, that sometimes happens with modeling toolkit stuff. That's basically just the show function going haywire. So you just have to put a semicolon at the end and it won't show it. Um, all right, so I've got this result observable. Now, whenever the stored string inside the text box changes, I want to parse the value. So I parse the string into a float 64. And then I'm going to update my result. Stop equals 10. Tinf equals val, right? So this is going to change the ambient temperature. Now I'm going to plot the result observable in the figure. Ah, okay, so you see here, what's happened is that the axis is taking on the width of the text box because we've said that the text box has its tell width equals true. So here we just say tell width equals false, and now that's full width, right? And so I think by default, the ambient temperature is 300. Let's make that 310. Ah, did I write something? Ah, right. I did write something wrong. That was supposed to be world, not transient analysis. Sorry, my bad there. Okay, just going to run through that again. All right, so this is now, you can see this is bottoming out at 300. I can now write 310 up here, hit enter, and there's another error. Huh. Ah, I forgot the underscore. Yeah, sorry about that, folks. So you can see that that took a little bit of time. And that's why I said this is sort of the obvious but kind of inefficient way. Because when you call this analysis, your entire model has to get recompiled, resimplified. It has to generate the function that it's actually going to execute, and then it has to solve everything all over again, right? And so even if I take this back now to 300, well, it took a bit less time. But especially for a complicated model, you don't want to be doing this. And so the way to do this interactively is you actually you have to go sort of lower into the modeling toolkit level. And so let's say, let's create this model called hello. We're going to invoke the function mpkcompile on the raw model to create what's called a simplified model. And so that's the model sort of after compilation. If you're familiar with the causal modeling, this is after tearing, all of that stuff. Then you create a problem. So the problem is an ODE problem. And this is the time span. If you want to add any parameter overrides, they go in here. But we will show another way to do this as well, right? And then you solve it. So sol equals solve prob. And if you don't provide an algorithm here, that's just the default algorithm. Otherwise, you can also say, I don't think, yeah, I don't think that type is available. I have to go through some hoops to get that, but that's fine. So, okay, so we got the solution here. You can also just plot this solution in the same way, right? Now what we're going to do is, oh boy, should not have done that. This is an abstract ODE solution. Okay. Semicolon, just to be safe, right? Oh dear, what did I do? Oh, okay. Okay, this works. So you have to go a bit down in there to get the type, right? But so now you've created the solution observable. And what you're going to do is, all right, so this is the same structure as sort of earlier, right? We've got the figure, we create the text box, but when we receive the value, we're going to do something different. We're going to say, so we're going to access the problem that we created here. And then we're going to say, we're going to use remake. And so this remake function, what it's going to do is it's going to, in a much cheaper way than recompiling the whole system will, it's just going to recreate the problem with these new parameter values. Right? And so I can now plot the solution observable. Ah, right. I forgot to actually solve it and assign the solution. Okay. Well, thanks AI. The AI figured it out for me. So, okay, so I've now got the solution observable, right? And now I can plot that. And it's interesting, you'll see this wiggling. This wiggling is actually caused due to the tolerance of the solver. So it's not actually an issue. It's within the tolerance band, but it just looks a bit odd. And you could choose a different solver, like an implicit solver, and that would make it go away. For this particular problem, then that has other issues. So let's see, this is 300. Let's make it 310. Huh. Okay, looks like I did that wrong. Well, it was working when I tried it a little while ago, but I guess something must have changed. All right, so check the documentation for that. Huh. Okay. Maybe I have to use the simplified model. Ah, there we go. So I was using model when I should have been using simplified model. Okay, so now I can change that to 310. I can change that to, 319, and that's quite fast, right? So this is sort of your very, very super basic the bones of a super basic parameter sweep. And let's instead of using a text box, right? Let's do all of this setup, but make it a slider instead. And the way you can do that is you just create a slider grid. So the label is T infinity. Okay, range to 200 to 400 sounds good. Start value at 300 also sounds good. And then, all right, so just recreate everything first. Now I can slide around. There you go. And so this approach will work for any number of parameters and any number of variables that you plot. So let's suppose now I want to do, instead of just changing T infinity, I want to change T infinity and T0. Right? So I do the same thing, but instead of only changing T infinity, I will now also change T0. And so I lift on both of the sliders values. And let me make this a little bit easier to read here. Right, so I'm setting both Tinf and T0. So let's see how this works. Okay, I'm going to warm this up quite a bit. Oh, that doesn't seem to be. Ah, sorry, instead of on, this needs to be on any. All right, so we're going to warm this up a bit. Right, and you can see that that also takes quite a bit longer. So yeah, there you go. Now you have a two-parameter explorer, which is solving the model um, sort of on quote unquote online, right? Instantaneously. Um, so yeah, that's the sort of basic parameter explorer kind of thing. The other interesting thing you can do with Makie um, is you can also do things like phase plots. So over here, I had this control oscillator model that I showed before. Um, and so with the controlled oscillator, let's see, I'll have a weak damping analysis. So I have a system called test weak damping, which basically just sets the PID values to something. Oh, what happened there? Huh. Right? And so that sets the PID values to something, and then so you can create the system. You can actually just run the analysis directly in this case, right? So I can get the simplified model from this result with Dyad interface.artifacts. Right? So I got the result here. That's a transient analysis solution. I can get the reference to the model by calling this artifacts. Sorry, simplified system. That's what it was. And so basically every model can define a set of sort of artifacts that it wants to expose to the user. Okay, so I can call plot on result, and this looks fairly boring. It's just, a sine wave. But what I can then do is I can then provide a keyword argument, IDXs equals, let's see, model dot, all right, let's see what this is. Model dot system dot, um, I guess one could plot both positions, right? So model dot system dot mass. Let's see what this is. Okay, great, this exists. So now I'm only plotting the positions of the mass in the spring. Ah, the spring doesn't have a variable called S, but I can check what it does have if I just paste this in here. Dot B, right? So maybe I plot velocity instead. All right. So here I'm not entirely sure what this is. So I'm going to ask my trusty AI agent to do this for me. Ah, okay. I guess we're running a bit low on time, so I'm going to sort of speed run this. Oh boy. All right. All right. So I'm going to ask so this is Dyad's AI agent. I'm going to ask it to go and look inside the controlled oscillator model and tell me which variables I want for a phase plot. So it's gone and read this and it said, okay, mass.s and mass.v. All right. Really? Oh, okay. So if I call this with square brackets, then that just plots them in time. But if I call this with parentheses, then that plots the phase plot. So yeah, there's all sorts of cool stuff you can do with this. And then let's see. I think we also have. I'm going to let this run for a second, and hopefully this works. But there's also quite a few GUIs that the control systems folks have made in order to basically, so you can design your PID autotuner and you can like live tune what's going on and things like that. Um, but yeah, so while that's happening, and because that usually takes a while to run, I wanted to show some cool examples of things that we have used Dyad and Makie together to make. And links to all of these will be in the email that we send at the end of this webinar. So this is a satellite orbiting the Earth. And what you can see is that this yellow line is connecting the satellite to the sun, right? So that it's got some solar panels, and that's when it charges. And when it, basically whenever the satellite is constantly consuming energy. So in Dyad, we're simulating the energy consumption of the satellite and its charging and the heat and the thermal system and how it gets heated by the sun and so on. And basically the idea here was to ensure that the battery never falls below 20%, which it seems like we've kind of done. Um, but yeah, so this is completely interactive, right? The satellite view down here is actually always pointing in the direction the satellite's moving in. So you can see, okay, there we go. Oh boy, this is quite a big GUI. So yeah, this is one thing. Now, another cool thing that we have, and this also started, I'll show that in a second, is we've got quite a few of these web dashboards that are made with Makie and a Makie adjacent software called Bonito.jl. And so this is a web dashboard for a simulation of a robot. And right now, the tools to sort of do these kinds of dashboards in Dyad are very manual. But hopefully coming pretty soon in the next couple of months, we'll have the tools to make this really easy to do and specify and for the parameter management and things like that. Um, And so what you end up, so let's say we wanted to change this TD parameter of the PID, and I make this 0.14. I hit enter. And you can now see that the behavior of the robot is qualitatively changed, right? Because that live updated the PID parameter to this new value. And I can also make this 0.10, right? So that's a bit lower. And then with that low amount of feedback, it seems to be finding it a bit difficult. It's got to make a lot of corrections to sort of keep on the set point, which is this blue line. Similarly, over here, we've got a digital twin for a sewage pumping station. And so I can hit the start button and that kind of starts filling up. The inflow is 3 liters a second. And you can see that this tank is slowly filling up. And at some point, I'll just make this 10 to make it a bit faster. Right? At some point, that tank overflows and then spills. And you can also introduce a blockage into the pump. So let's say that one pump is 10% blocked. That makes it even faster. So yeah, this is a Makie figure, right? These are Makie figures, but then these are actually just regular web components. So you can also do that kind of integration. If you want to learn more about this and try it out, I have a very, very basic thing that does this. And so 1 second, sorry. Let me try and send this link in the chat. Okay, we're getting close to an hour, right? Yeah, so I've sent a link in the chat, and just one last thing I want to show before we open it for Q&A is this thing. So this is still a bit big. I think this was designed for a much bigger monitor, and I hadn't been able to try that before this. But yeah, this is a pretty complex visualization, which is basically just controlling the PID autotuning. So I think, yeah, because the resolution is a bit weird, something probably went wrong there. And unfortunately, we didn't have a scroll bar. But yeah, you can also do, like, there's a lot of parameters here, right? This is showing you the optimized parameters and things like that. There's a run button all the way down here that I can't actually reach. So yeah, thanks everyone. And yeah, open to any questions.
Yep, you can type in your questions in the Q&A section, and Anshul will pick them in the order that we receive. Okay, it looks like we don't have any questions, so maybe we can call it a day. What do you think, Anshul?
All right, yeah, no, that
Yeah,
should work.
yeah. So
Yeah, if anyone has, just as a side note, if anyone does have like a question they want to ask about how to visualize a dyad model or what you can do with visualization in general, there is a dyad channel on the Julia language Slack, which I'll also put in the chat. Let me, sorry if I can just find it. Or if you go to the help.julia, if you go to the dyad documentation page on the top right there, there'll be a Slack icon. And so you can click on that and that'll take you to the invitation link. But yeah, feel free to ask there or ping me on Julia Slack or Discourse or GitHub. And yeah, thank you for joining.
yep, thank you everyone for joining this webinar, and we'll send the recording to an email to all of you, and this will also be available on our website in a couple of days' time. We have a couple of more webinars lined up. You can check it on our website in the events section, and we hope to see you in our future webinars as well. In case you have any questions, you can write into us, and we will reply to it as early as possible. And thank you, Anshul, for this insightful session. And thank you, everyone. Have a great day.
Awesome. Yeah, no, thanks, Sanjeev. Thanks, everyone.
Thank you.
Hope to see you later.
See you.
Bye.
Bye.